This is EE 569 on Friday, August 30th, 2013.
Also, we have a discussion class, and will be taught by TA. And this is very important for your homework. So it will be a very big part of the course is the programming assignment. And so I know a lot of you not very familiar with the programming tools, but it's extremely important for you. Particularly, you want to be competitive in the job market. The programming skill is very, very important. And many students take this class because this class has a lot of opportunity to practice the programming. And so you have to be ready, okay, at least mentally, ready for the challenge. Okay, but it will pay off. I assure you, if you work hard, you will gain a lot. You will gain a lot. Okay, so the discussion, I tell the TA they need to spend 50% time in the discussion talking about homework, helping you in the homework. And then another 50% of the time teach you something, some supplemental material, so some extension and so on. Okay? And yeah, I think the content will be important. And also there are two rooms. I think basically say you need just go to one room. The other room is for the overflow room. Because we have right now about 110 students enrolled, and each room is less than that. Each room around say 50. So they need to assign 2 rooms for that purpose. So one is called the overflow room. So the TA will give the instruction in one room. The other room, just in case, one room totally full, students can go to another room by watching the TV. But usually, in the middle of the semester, you will not see many students in the classroom. So maybe one room is enough. But we cannot use that assumption. You know what I mean? We have to assume everyone will attend throughout the whole semester. So there will be 2 rooms. And so that's the situation. Okay, so it's not a conflict. Some students say which room I should go. Either room is fine. Okay? But of course, if you go earlier, you want to go to a room with the person in front of you, right? Not just through the TV. So if you go earlier, go to the room with the TA. And I believe it will be the 136. Okay. So there is the DEN website. So you can check all the announcement, all the homework, including this syllabus. This course syllabus, all there. So you can get that. And also there will be discussion board. So a lot of Q&A you can see from the DEN discussion board. So maybe you find some problem in your homework, but you go to see discussion board. Maybe already some student raised the question and been answered by the TA. Okay, so you don't have to ask the same question again. So take a look at that. My office hours are Monday and Tuesday, 8:30 to 10. Some people say, why so early, 8:30? Because some students come the first class at 9 o'clock. So you can come to see me before your first class, right? So 8:30 and 8:30 to 10. But if you have a problem related to your homework, you should ask the TA for the help. There are 2 reasons, okay? So one reason is the homework designed by the TA, not designed by me. Okay, so a lot of homework, I reviewed the homework. I went through, but a lot of details the TA knows. The TA designed the homework. The second, I did programming when I was a graduate student, but that's about more than 20 years ago. And I never programmed after that. Okay? Once I got my PhD degree, I started to teach. I never do any programming. So if you ask me any programming questions, honestly speaking, I cannot answer you. Okay, I cannot answer you because I haven't programmed for 20 years. So you don't want to ask someone, take me, even look 2-line code. I need to spend a lot of time figuring out what you are doing, right? But anyway, if you go to the company, all the high-level managers, they never touch the program anymore, the same. Okay, so I'm not an outlier. So for those programming assignments, definitely you will get much more help from TA than from me. I can tell you the algorithm side, high-level algorithm, this is the way to do. But come to the implementation, I'm really not that good. Okay, so I have to be honest to that. So there are 3 TAs for this class. I'm not sure everyone here. Sanjay here. Okay, he's an experienced TA. Okay, and he has the office hour. You know, every TA has 2.5 hours weekly. And another one is Sachin Chachata. Sachin here. The third one is Hyunsup Ko. Hyunsup is here. Hyunsup, yeah. Understand? Okay, so Hyunsup is there. So every TA has 2.5 hours office hours, and it's on Monday, Wednesday, and Thursday. And Tuesday will be the discussion time, Tuesday discussion, and then Friday is the lecture time. Okay, so that's covered, pretty covered. And there is a room and the phone number for the office hours. So there are 2 graders, Wei Hao Gan and Fang Jun Pu. And both of them are excellent students from 1 year earlier, so the fall last 2012. Okay, so they took the class, and they know this, the grading standard and so on. And also ask them, the same problem will be graded by the same person. Say homework number 1 is 3 problems, so your problem number 1 will be graded by 1 grader. You know what I mean? Just the same grader will grade the same problem for everyone. So that to be fair, okay? So if the grader tougher on you on 1 problem, then it's not because of you, but you just apply the same standard to every student for that problem. Another problem, second problem, will be another grader, and so on, okay? So grader will not have office hour until they graded the homework. So immediately after the grading homework, the grader will grade. So now the time frame I asked them is, if the homework now is due on Sunday night, midnight of Sunday. In the past, it was Friday afternoon, 5 p.m. Then I found one very strange, but actually it's also normal phenomenon. Is Friday morning, very few students show up in the classroom. Everyone working in the computer room because the Friday 5 p.m. homework due. So now I changed that purpose to Sunday midnight. So Friday you have to show up, okay? And so midnight, 11:59 p.m. So you have to submit the homework at that time. Okay? So then after that, the grader has to return the graded homework. Basically, it's all website. Okay, so you submit everything website, no paper, and grader will give you the grade also on the website. Give you the grade, what's the score for each problem within 1 week. So 1 week, the grader has to grade the homework, and then after that 1 week, they will post the office hours, and then you can go to see the grader and ask the grader about questions if you have any questions about grading. And also, another thing I want to say is that many students feel they finish the program, they run the code, they get a result, and their job is done. But they get a lot of points taken away, so they were very unhappy. But the key is the discussion. You need to show the images, show the figures, and you also need discussion. You know, particularly also like students from Asia, and maybe not very good at play or not good in the English. So they don't want to do a lot of discussions. They just say, well, you see my result, you know what I have in mind. No, you don't discuss. No one will discuss for you. The TA has no responsibility to guess what you have in mind. You know what I mean? So a lot of things about look at image, look at figure, and you have to make a discussion. This is better, that is better. This is something you have to make discussion. Otherwise, you get point deducted. Don't feel strange about that. Okay, so discussion, writing some English also important. Okay, so you are welcome to communicate with me, with TA, with grader by emails. But then in that email, you put the E569 in the subject line. I receive virtually 100 emails a day. Okay, so don't think your email will easily be spotted by me. So many emails, and I have to delete many emails even before I start reading. Okay, so I don't want to just delete your emails, because I somehow, didn't pay enough attention. Right? But just so many garbages, so many other things. So anyway, put the EE569 in the subject line. The book is the book by Bill Pratt, the Digital Image Processing. This book, 4th edition. Okay. The book actually quite easy. The material I'm covering is more difficult than the book. But it's hard to find any really good book right now. There are quite a few books, but some are too mathematical, not good for the beginners. And this book, I think some material really, I would say not that updated, but but I think it's friendly, easy to understand, so that's a good thing. So you read, you will not have a lot of problems. There are some books just too mathematical, and then you really cannot appreciate as much. This book is more algorithm oriented, so it has some method. But we will cover something much deeper than the book, okay? Much deeper. So there will be some papers and so on for you to read. So there are other reference books. So let me just go quickly over that. So the first book is about the Dungeon and Serial. And this is really about a multi-dimensional DSP, and consider image processing as a two-dimensional DSP. But today, actually, I'm totally stay away from that view. I don't think image processing is considered as a two-dimensional digital signal processing. I don't view DSP usually talk about time series, the time domain signal processing, 1D. And image processing actually has very little to do with time series. Okay. I don't view it as a two-dimensional generalization of the time series. No, I don't think that's a good view. Image processing is just image processing itself. So DSP and DIP actually is very different. But when I was students 30 years ago, they feel image processing just extension of DSP. But right now, I feel there's really they are very totally decoupled in some sense, totally decoupled. So I don't even want to teach you about 2D transform, Fourier transform. I don't care. For those transforms are not important at all. Okay, so better book is by Enio Jen, Fundamental of DIP, in 1989. But this book is it's good. Okay, there are some mathematics, but the problem is there are a lot of typos, a lot of errors, typos in the book, and the author died, so no one did any update on the book. Okay, so I think I don't want to confuse you by using this kind of book with a lot of typos and so on. There's another one by MIT Professor J.S. Lim, Two-Dimensional Signal Image Processing. When I was a student, I used the draft. Even there's no book yet. It's just early version. It's draft for this book. But actually, I don't like that. So there is also more open use one is Gonzalez and Woods, DIP, 1992. So yeah, but again, it's quite old now. It's almost 20 years. And there are also other books like two-dimensional imaging. This is more about analog processing, and another one, digital image processing. And there is a new one by Alan Bobick, UT Austin professor, and it's very thick. And again, I think it's very hard to find the book I really want to use. So I think you just follow my lectures. Okay, come back to the homework. This is the most important part. You should pay attention. So I will give you 4 homework projects. This is one more than the previous years. In the previous, it only has 3 homework projects. But right now, this year has 4. And the one I take away is the term paper. The term paper, we used to have 3 projects on 1 term paper. Then, after my observation of many years, people sort of very, very sloppy in writing the term papers. Most students didn't do anything until the last week of term paper and submit something really like a very poor quality term paper to me. So I feel it's really a waste of time. And I didn't give students good training. So now I just abandon that term paper. So I will say I give you 4 homework projects. Just make everyone work hard from the beginning to the end of the semester. Okay? So, well, you may hate me for the time being, okay? But you will love me when you get a good offer. You say, I get this offer because the professor will give me good training. Okay? That's the most important thing. So I don't care about short-term and satisfaction. I care more about long-term happiness for you. Okay? So it's a 4 project. So each homework, say I call it project, but actually each homework has 3 problems. So you 3 times 4, you get 12 programming assignments. So 12 means almost weekly. Every week you have 1 programming assignment. Okay, so, but again, you can learn a lot from that. And also I asked here in this method, we start with something it's called 65% of the homework will consider basic. So each problem you can see like 1A, the problem number 1, part A, they say basic. So basic means I expect you be able to do that without any difficulty. It's straightforward. Okay? It's straightforward. So basic. Because some students doing the following. They do the homework number 1, say the homework number 1, problem 1. And then they don't have time for problem number 3. They just don't do it. You know what I mean? They just have time to do the 1A. They do the problem 1A or 1. And then they leave the problem 3 totally empty. And this is not good. I would rather students do all the basic part first. Problem 1 basic, problem 2 basic, problem 3 basic. And then you go to advanced. Do you know what I mean? Sometimes students just get stuck by the first problem, the advanced one, they get stuck. Then they don't do anything, problem 2 and 3. So that's the purpose. I divided each problem. There is the basic part. You should get the score, right? And then advanced one, you know it's a little bit tougher. So if you are not able to handle it, don't feel too bad about that. But it's an advanced one. So I tell them you need about 65% basic ones, 35% advanced ones. That's for good students. If everything too simple, I cannot differentiate, right? So the advanced one. And also I'm kind this time that 10% called the bonus point, bonus problems. So you add them together, you get 110%, more than 100%. So some students don't do well, didn't do well in the midterm. And they all ask, Professor Guo, can you give me some extra credit? I do extra service, I do extra things. I said, no, I don't have extra thing for you. If I do offer that, I have to offer to the entire class. I cannot offer that to you particular person. You know what I mean? One person asked. He asked, I give him some extra assignment, but the students don't ask. They don't know. So this semester I'm very fair. There's extra bonus for everyone. Okay, so if you want to do it at the 10%, you can do it. But I say, what's the final thing? Final thing is curved. The final thing I will do is, for all the students, if their final point above 100%, they get A+, right? A+, there's no A+. So A+ is the same as A, okay? But that's at USC, A+ is the same as A. There's no extra, just 4.0 is the highest. But I can write down A+ in the sheet, but it will be truncated to A. By school, okay, by university, not by me, but I can. But anyway, those students, it has the final score more than 100, they truncated 100, and they will not consider part of the curve. So I will take that group out. Okay? Assume there are 100 students and 20 get more than 100. So 20 all get A. Okay? Then the remaining 80, I curve that. I will give about 50% A, 50% B, something like that. That's the normal distribution, is about 50-50 for that. Of course, there are some outliers will get a C, okay? I don't guarantee you will get a B, but there are some outliers maybe get a C. But what I want to say is, indeed, if you doing very well, you belong to the first group, it's above 100, your total score, then you automatically go to the best group. And other students will not penalized by that. You know what I mean? Other students, you don't curve something lower than 100. So some students are very good and so on. Those students actually will not be participating in the curving. Is that okay? So I try to encourage, okay? Actually, I can be very honest, is when I conduct the teaching, I'm very tough. But when I'm giving the final grade, I'm very sweet. And the reason for that, balance that is, you're working hard, you deserve. You know what I mean? You're working hard, you deserve. So I can be given more A, and I can talk to university and say, these students all above 100, can you do anything about them, right? They are so good, right? So something like that. So anyway, you just have to try your best and take the opportunity to get some kind of bonus problem. So each homework, actually, total score is 110, each one, okay? Any question about this? So you are happy? So basically 440, right? 440 points for that homework side, okay? So then there is one midterm. It will be November 1st during the class hour, Friday, during the class hour. So that's the one midterm. So grading policy. So there are 4 problems, right? 4 projects or 4 homework sets. Each one will be 18%. So totally 72%. Midterm is 20%. So what's the remaining 8%? Okay. Remaining 8% actually is knowledge and quality of your submitted code. So what's this? Actually, each homework you can view it like 20%, but I leave the 2 points to the end. So when the grader grade your homework, basically mostly is look at the final results, like your performance, your curve, your image quality, those kind of things. But then there is a program quality. So some students write an extremely messy code, and some students has a very nice code. Okay, so very, very professional code. So I want the TA and grader to take a look at the quality of your code, and also the knowledge of your knowledge of the code. Because again, there are some people in the past, they took someone's code. Okay? And this is sort of very, very sensitive issue for the software-oriented class. When the class emphasizes a lot about programming, particularly computer science, and if students submit someone's code, basically they don't have to do anything, right? So this is called plagiarism. So you will serve dual purpose. One is whether you are the author of the code, and how the people know. They just go to your submit code. You submit code already. Each time you have submit your code, they just take arbitrary random select part and say explain it. And you are not the authors, you may not be able to explain, right? So that's one of the things you will get point deducted, at least at that point. And the second is about your programs. Is the program too messy, or the program is very well written and structured document? So this is about the programming part. So it's like a 2% for each homework set. But cumulative is 8%. So 8% will give 1. So also I want to see the progress. Some people may do the poor code in the beginning, but along the time, the code becomes better and better. Then you will get most of the 8%. You know what I mean? You don't have to be excellent in the beginning, okay? But I want to see the progressive. If you do better and better along the time, then you show you are doing better. Then it's fine, okay? So this 8% is we wait until the end of the semester, and we check the overall whether you are becoming better programmer or not, and so on, and we'll give this 8%. Any question about this? We will talk about that. Yeah, just wait a little bit. Okay, so these are the, so for the 72%, of course, you can go more than 72 because there is one more than the 10% bonus. So you can maybe go to 80 something. It's possible. Okay, it's possible. But just a percentage like that. So these are the schedules. So the homework number 1, due date, homework number 2, number 3, number 4, okay? So it's Sunday, 11:59 p.m. So you submit the code, there is a timestamp, there, okay? So now I want to talk about the languages. Okay, so I think one thing I want to talk is about the late homework. I didn't say anything. In principle, late homework is not counted. So you basically get a 0 for the late homework. Okay, so that's basically the principle of the class. But every semester, every year, I always receive some student giving a lot of, heartbreaking stories. Something happened to the family. I don't even know. I'm not a detective. I'm not responsible for checking all your claims. Okay, and sometimes doctors, some special notes here or there. So what I will say is, in principle, no late homework. Okay, late homework will not be accepted. But in practice, I will do the following. You submit things, there's timestamp, right? So there's timestamp. And then I will not tell you what I'm going to do until the end of the semester. Or I have to say, I tell you it's 0. But maybe I'm more graceful than 0. Maybe I can give you some partial credit. But you have to under my mercy. And I will tell you my graceful policy at the end of the semester. I'm not going to tell you every time. Actually, the thing I have to say, there are several considerations, okay? The one consideration is habitually late. Student late in the first homework, always late, no, not always, often late in the second homework, often late in the third homework, and so on. Those kind of habitual late behavior is totally unacceptable. So I want a window to observe your performance. If you continue late, then I really give you 0 everywhere. But if you're late once and for special reason with a doctor or something, note, then I will believe you because that's really a special event, the doctor and you are sick or something. So then I can be nicer to you. So I'm not going to do a short window decision. I want to see the whole semester, and then I will see whether you deserve or you say every happen to the homework due, you are sick. Or something bad happened to your family every time. I mean, I cannot believe that, right? So do you know what I mean? So so there is a certain way I can look at the pattern, and I'm doing sort of machine learning, data mining, those kind of research. So I can mining your behavior, and I will say, can I trust you or I cannot trust you? Okay, so don't ask me about anything for the late homework submission. The official answer is 0. But an official answer is, well, wait and see. Wait and see until the end of the semester. And then I will decide how much I'm going to take your points out. But one thing is definitely 0 is after homework being graded, then it doesn't matter you submit or not. If after 1 week, everyone homework being graded, you will submit, it will definitely be 0. Then there is no even wait and see, okay? It's just 0 for sure. Is that clear? So that's basically you have only 1 week window you want to submit late homework because it may be still considered. But after 1 week window, everyone homework been graded and returned, then you don't have to submit because you will not be graded at all. Any question about that? No questions? So I don't want to receive any email about this again. Professor Guo, I have to submit my homework late and so on. I told the policy in the first lecture already. You think it's fair? Yeah, I try to balance, okay, because I teach in the class for almost I would say almost 20 years. I see all kinds of behavior in the past. So I do a lot of preventing job. Okay, okay, about languages. Basically, there are 2 choices, MATLAB or C++. MATLAB is more convenient to handle data structure. So you save some effort with the data structure. But you cannot call a lot of functions in the MATLAB. MATLAB has some function, .m file you can call. And when you call that function, you simplify a lot of programming tasks. But this is not the application oriented. I want students to know how to implement things. Even basic function, you need to implement. For example, histogram. So C, you need to write down the histogram. And the MATLAB, you need to also to do the histogram calculation. You cannot just call the histogram subroutine. Is that clear? So MATLAB simplifies things in terms of the a lot of data structure, right? IJ index and so on. But it's really not the one used in the industry for the multimedia field. MATLAB is useful for the signal processing, for the communication. If you go to Qualcomm, you can use MATLAB. But if you go to Google, you go to Facebook, and you're doing the multimedia, sort of image video processing, no one uses MATLAB. It's too slow. Let me give you an example. One of my students working on MATLAB code for one like a fingerprint detection, 40 minutes, 40 minutes. Then do the C 1 minute. So if you use MATLAB, actually, a lot of results will take much longer time. You wait there 40 minutes to see the final images. You use C, you get 1 minute, you see the final images. You know what I mean? So the difference between the MATLAB and the C is huge in image video processing. Communication or 1D signal processing, the difference gap may be 1 to 5, but here it's 1 to 40. So there's tremendous difference in the time. So no one really uses MATLAB in the industrial code. Even communication company, when they want to do quick prototyping, they want test algorithm, they do MATLAB. But once MATLAB function well and so on, they still convert to C. You know what I mean? So in the product code, it got to be C. It cannot be MATLAB. MATLAB just quick prototyping. But for image video processing, even MATLAB cannot be too quick. Cannot be too quick. So I encourage you to do C, C++. And again, if you want to benefit from the programming training from this course, you better don't use MATLAB. MATLAB will not give you some advantages. You will use C, you'll get more advantages. But you can use either one of two because some people say, well, you know, I'm a communication major. Okay? I only care about communication. And then image processing, just one course I want to take in the multimedia area because, for example, you are famous, I want to do this with you. So, okay, but for my rest of my life, I'm not going to touch any image video processing. Why should I learn C? Okay, in that scenario, of course, you can use MATLAB. Okay, so but for other people, you think you want to work in the image video processing field, you got to be serious. You got to be serious, and this is the opportunity for you to be serious. Okay, so you see. So you are encouraged to use C, C++, since it's commonly used in industry. If C, C++ is used, so I'm using the carrot approach, okay? Stick and carrot, but here I use the carrot approach. If you use the C, C++, you will receive 5% bonus point. And this 5% based on your raw homework score. So in other words, if you have do everything very well, you get 110, right? 110, you times another 1.05. So you smile big, right? You know, everything's so good. So the C part, I will based on, but if you say 110, but you only get 50, you make a lot of mistakes in the homework. You only have 50 raw score, then you just 50 times 1.05. You know what I mean? So it's your raw score times 1.05. Okay, so that's if you use C. So any question about this? Yeah, we use each problem as one unit. Okay, so if you one problem you have some part MATLAB, some part C, we just treat the MATLAB. So if the whole problem, each homework has 3 problems. Each problem independent. So when you use C, this problem you will get a 5% bonus for this problem. Okay, but there is another problem. If you don't use or use a mixed hybrid, whatever, then that's a separate thing. There are some special cases I will mention in the homework. There are some special cases because I ask you to run some source code from the internet, and the source code is MATLAB. Then in that case, you don't have to worry about that. Okay, any question about this part, programming languages? You know, I find all the opportunity to let your score become higher and higher. Do you see my efforts? I give you a lot of extra things rather than take a lot of points. So I try to be more encouraging in that sense. But of course, after you read the first homework, you will feel very depressed. Because the first homework is challenging, right? But anyway, it's just a balance of the two. Finally, the most important thing I feel I have to emphasize, every semester I encounter cases like this. every semester. So I have to say no exception in the last several years. All that means what? Students being caught of plagiarism. So basically, two students had very, very similar code. So part of the code just compare. Every semester we pay attention to that. And you know, once this been detected, students came to my office, all tearing and say a lot of things, but there's not much I can do. I only can give you warning in the very beginning of the semester. Please do not do it. And I know students sometimes they are lazy, they don't work hard until the last week before the homework due. They start to do the homework. They're under tremendous pressure. Then they're under the tremendous pressure to getting someone's code. And not all getting, usually you probably not getting from your colleagues, then you're getting from students from previous year, previous 2 years. You figure out the way to get the code, okay? But we also figure out the way to preventing that. And so we have all kinds of algorithm and method to find the similarities. Like police and the thief, right? I'm not sure I can catch 100%, but if you're unlucky being caught, we'll report to the university. We'll report to the university. There's no exception. Whenever your case been caught, there is enough proof. Even you don't agree or you agree, it doesn't matter. I just show the whole thing, the whole proof, all the programs, and submit to the university. And I know some students under the pressure to give code to fellow students, but I'm not going to differentiate who is the provider, who is the receiver. It's the same, okay? It's the same. So please do not give your code to other students. The penalty, the punishment is the same. So you keep your code well. Someone say, oh, I went for the lunch and I leave my screen there, and so my friend, who will believe that? You think other people are idiots? When you go out to lunch, of course you shut down your computer, right? Why you leave your computer screen open? So don't tell me all that kind of, you don't even believe yourself. Okay, so this is, I would rather you not taking the class. I don't want you being caught by plagiarism and then you regret at that moment. That's very, very bad to everyone. I don't feel good about that. You don't feel good about that. But I need to be fair to all other students who work extremely hard. I would say 99% students working extremely hard, right? So for those special cases, you got to either you just drop, you just drop the class or something. But please do not copy or please do not give your code to other students. Agree? This is so important. Because I hate to see all tearing students, but every semester I see that. So I know what's wrong. I didn't emphasize enough. So every time I try to emphasize that. But every semester I see cases. So please do not do it. Please do not do it. This is a big no-no. You just cannot try. In the university, in a good university, you pay a lot of tuition, but you want the university has a sort of integrity system. So you get an A, you deserve the A, and A means something. It's not the A is like fuzzy A, it's gray A, the A, contaminate. It means what is contaminate? Because the professor doesn't enforce the rule well. The professor just so nice and don't check the code and so on. It's not a solid A, right? So we need to work for the integrity of the system, for the owner. You graduate from USC, you graduate from my class, you get an A. That means you are good. You cannot steal something from this class. Okay? So I think it's everyone's responsibility to keep the integrity of the class. And you get an A, you should be proud of that. Okay? I know there's my homework is over the internet from previous years. You go to the EE569, type that. There's some homework there. I don't know who posted that. It's of course not me. But someone posts my homework, someone may post some code. It can be found from the internet. I know that. But if I can find that, I could put that code into the database to search the similarity. Okay? So you don't say, well, the code in the internet, someone is to be put there, so I just use that one. Sorry. Whatever, you just have to write your own program. No matter there's outside things, it's all treated as bad factors. You don't want to be attracted by that kind of bad influence. Okay? Also, each year I ask the TA to change 50% of homework. So the TA has to be changing the homework because the website has my homework. Right? So I cannot just duplicate. But change 100% is too much. So I ask the TA, say, change 50%. So there are some new homework and so on. But that's all I can do. I cannot go too far from that. Okay, any questions? Yes? There is no final. No final, only one midterm, 20%, and four projects. Each one is like approximately 20%. So total is 100%. But everyone, a lot of bonus here, bonus there. So you can leverage the bonus. Actually, I think one thing is midterm actually has a bigger variance. Some students just don't do well in the exam. So the midterm has a bigger variance. The homework, as long as you work hard, you know, but it's really something you learn materials by doing the homework. You learn the material. Okay, so we will start the first lecture. So there's no more questions, right, about the administration of the class? It's posted already. It's posted. And I will talk about that today. Okay, so that's the first lectures. Okay, operator, can you show my notepad? Show the notepad. So before everything, I call it like chapter 0. It's a digital image representation. So usually there is a so-called basic unit. We call it the pixel or pale. So this each is like a point for data. So we call it a basic unit. And this basic unit in the image processing context, we call it one pixel or one pale. And at this location, we have the, depends on the, it's a grayscale or gray label images. If the grayscale images, we have typically the 8-bit images, so grayscale or gray label. And typically it's 8-bit. But of course, you can have a higher resolution. You can have 10-bit, 12 bits, it's all fine. But 8 bits. So 8 bits, you can allow the 2 to the 8 values. So 256 values. So you start from 0, 1, until 255. And if a grayscale, gray label image, we call this like brightness. Brightness, okay? And 0 is the darkest. And 255 is the brightest. Okay, so if you do the 8-bit representation, this is 8 zeros for this. And this 255 is A1. Yeah, so you have A1, that's the brightest. So 255 is like totally white, and 0 is totally black. And this, in something in the middle, is a grayscale, from very dark to very bright, and to the brightest. Okay, so that's 8-bit images, gray level, grayscale images. And sometimes people call black and white images, but actually it's gray. It's not only black and white, it's a continuous, at least you have 256 labels. And if you have color images, usually you have the 3 color channels called RGB. So R is red, G is green, B blue. So you can, each channel you can also have 8-bit. So totally you have 24 bits. 24 bits. And so in terms of the combination, so you have 256 label times 256 label times 256 label. That's called the true color. Right? So red, you have 256 labels in terms of red, green, and blue, and so on. So 24 bits. So that's equal to the power 24. And so you have this kind of raw representation, no compression whatsoever. And in the image format, this is called the BMP format. Okay, so the BMP format, .bmp. Okay, so you have the true color and so on. So when you try to represent that, so there is each pixels, and each pixels carry some kind of values. So if it's a gray level scales, basically you have each pixel is just a byte. There is no location information. It's just order in this. It's called a row-wise scanning order. They use the fixed scanning order. They do this kind of scanning order, row-wise scanning order. So the first byte is the gray label for the first pixel. The second byte is for the second pixel, and so on, until reach the end. So this is called the width, the image width, and there is also image height. So image width and image height, okay? And so when you represent the images, operator, can you show my computer screen? Show the computer screen. Can you show the computer screen? So there is images given. You cannot. So let me just show you. There is a called a shape stored row, and there is an image file called this one thing. And they give you a format. For example, it's 257 times 257 times 3. So the first number is about the width. The second number is about the height. No, I think it doesn't matter. I already put down here. So next time I tell you, then you switch, okay? 3 means it's a RGB. So when you have an image file, you need to declare the width, the height, and also it's 1 or 3, right? Gray level or color. So that when I give you consecutive byte, you know where you go to the second line, right? You're starting from the upper left corner, and you go one by one until you reach 257. You finish the one line, one row, and then you turn back, go to the beginning of the second line, and again, row wide. So this so-called row wide scanning. And then you can finish the whole thing until you go to the end of the height. So then there is an index. So for images, so suppose there is a width is a m, the height is n, and we have index so-called ij. Usually this index along this vertical direction we'll call it I, and along this direction we'll call the index j. And I, the starting point is 0, 1, 2, until n minus 1. So I, 0, 1, until n minus 1. So going downwards. So this is different from the Cartesian coordinate. Cartesian coordinate is x is going from left to right, right? But the y is go from top. But here you're going downwards. So I, the first line you call I equals 0, the second line you call I equal 1, and so on. So each row is with index like that. So this is like a row index. And j also starting from 0, 1 until n minus 1. This is a column index. So this is a two-dimensional image coordinates. Ij is the image coordinates. And you can do the conversion. Say you can, using this, if you want to scan that, you can convert this 2D image coordinate into a 1D sequence, right? So you can do the 1D sequence. So the 1D sequence will be like j plus I times m. And you can call this like k. So this is converting, you're mapping the ij into k. And k will start from 0, 1, until m times n minus 1. Right, you're starting from 0, 0. So 0, 0, k get a 0. And then you start to, I still 0, and j is moved from 1, 2, 3, 4, 5. So until j to n minus 1, right? J to n minus 1. Then you come back, I equal 1, j equals 0. Is that clear? So you go this one and finish and coming back and so on. So then the k is like a 1D index, but it gives you the whole places, right? So there's a 1D and 2D index. You see, this, yes? The original one? Which one? Oh, this is the example. Just one image file in your homework. There's a, I say ask for the last page, but you know, so it is just one example. Okay, so you see this is simple, right? So far so good. You can do the first problem now. You know, after this, actually all this preparation work is for the first problem in the homework. Simple, right? So far so simple. But let's look at the homework. Okay. Let's come to the reality. Okay, so you can see how much you can do with this. Okay, you can do a lot with this already. I want to make it bigger. Okay, so this is the 569 homework number 1. And each homework has 3 problems. So now I talk about the first problem. Just by this problem is really warm up. It tries to let you to how to access the image point, how to read, how to write. And another thing important is you don't want to mix things into the same file. Whenever you read from one file, but you write another file. Don't replace it. Don't write on the same thing. So this homework, let me just put the comments here. Problem number 1. It's really an exercise for image read and write. So you try to do image access. Read means you try to access, and write means you output. So the whole thing designed for this purpose. So make sure you know how to manipulate image. You can read, you can write. Is that clear? Is that the important task? I mean, you have to start from here, okay? If you cannot do the read and write and then forget everything afterwards, this is a fundamental, right? Fundamental. But a lot of students just you're not familiar with programming and just get so, scared by this kind of homework. Okay? But it's just beginning. Okay, you got to overcome those kind of barriers. Okay, so let me explain what's going on. Operator, I need to switch to the computer screen. Switch to the computer screen. Okay, can you see it clearly now? So the problem number 1, so general instruction, there's a homework guideline, MATLAB function guideline for more information how to complete and submit the homework. Again, US policy on academic integrity and penalties for cheating and plagiarism. Everyone has this kind of training class, right? Every new student, you need to attend a class about plagiarism, cheating, this academic integrity class, right? The video. Everyone needs to go through that video. So this rule will be strictly enforced. Okay? If you make any assumption about the problem, please clearly state them in your report. Okay? So come to the first one, so-called image manipulation. Actually, it's really not about image manipulation. It's about image access and output. So that's 33%. So in this problem, you will perform simple image manipulation, such as accessing pixel values, implementing and interpreting histograms. Okay? I will talk about histograms. So one is called a blue screen technique, and this is a basic 10%. So I say basic 65% basic, 35 advanced, 10% bonus. Okay, so it's all here. So this is your input images. You have a blue background, a blue screen, and you have some kind of a color, circle and square and so on, okay? And the desired output is something like that. You want to extract this object from these images, get that out, right? So how to do it? And then he says, well, the blue screen technique, can you read that? Or it's still too small? Let me make it bigger, okay? Will that be better? Can you see? The blue screen technique is often used to shoot special effects scene in movies. The scene is shot with blue background that can be easily separated from the foreground. So basically use the color property. Some human behave something, but of course don't wear blue shoes. Okay? Blue shirts, that's in big trouble. So you wear something not blue in front of blue. But actually when you go to a movie studio, usually it's green. The background is not blue. The background mostly is green. But then don't wear green shirts. Probably it's hard to find green shirts anyway. But anyway, so it's some color, uniform color in the background, and use a color difference to filter it. So there are some color, it's background, and some color is foreground. Okay. For example, figure 1A, this one, has the blue background that is different from the foreground, consisting of geometrical shapes and objects. For this problem, you are required to separate the foreground from the background, and figure 1b shows the desired output images. Note that the outside black border, this outside border, is actually not needed, okay? It's just used to indicate the image size. You do not have to add such a border in your output images, okay? There's no border. You just try to get the object out. That border just shows image size. Please discuss your algorithm in detail with the aid of print pertinent images and plots. Okay. In order to identify the background color, you can analyze the histogram or 3 channels of the original image. Now, these are color images. Okay, so in that case, each pixel has 3 bytes, and 3 bytes will be RGB. Okay, so if you look at the file, it will be byte, 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 a lot of bytes. But 3 bytes, the first 3 bytes you can say is RGB of the first pixel. The second 3 bytes is RGB of the second pixel. And another 3 bytes will be RGB for the third pixel, and holding the right row-wise fashion. That clear? So there will be no location information because it's fixed order. So just the RGB, 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 and so on. And when you turn around, depends on the width, right? When the width is met, then the next one will go down to the second row. Is that clear? So you need to write a program to read that file out and know it's RGB for the pixels, okay? So in order to identify the background color, also, you say this background color, what's this one? It's really just blue is equal 7 and the other 0, 0. I don't think so, okay? It won't be so easy. So you can analyze the histogram of the 3 channels of the original image. Let me know the background color is RGB, so there is some single value. But it's also possible that there is some variation in the background color. So then instead of using a single value of background color, you may select a range. So RGB, R between R1, R2, G between G1, G2, and blue between B1, B2. So there's a lower bound, upper bound in the range. So you allow the background color slightly vary. It doesn't have to be just the same. And you can say why this is the case. Because when you go to the real world, the studio, you're shooting something, there is a background, but how can you guarantee the background is just the one color? Right? There may be some shadow, there may be something, there are a lot of environment issues. So the background indeed will slightly vary. It's not that you do it on purpose, but just when you capture it, there is some varying background. Is that clear? That's practical. That's practical, not that you try to play the tricks or whatsoever. In practical world, real world, the background may vary slightly, but still the foreground color and background color are separable. You are able to separate them. They are not too close. If they are too close, you use the wrong background color. Is that clear? Okay, so now So let me explain the histogram. So, okay, can you show my notepad? Show the notepad, yeah, okay. So actually, some of you may have probability class, or you are taking the probability class. So actually, there is some kind of, whenever people talk about probability distributions, probability density functions, all those kind of things, that talk about random variables. So say you're random variables. Let me use some example, say age. So age of a group, and then the age is a random variable. And then we look at the distribution of the people, say all people in LA, living in Los Angeles. And what's the distribution of the age? Some people are older, some people are younger. So then you can look at the distribution of the age. And this distribution of age, you can view it as a histogram, and you also can consider this a probability function. But there are some slightly different viewpoints. Okay? Histogram is more in terms of statistics. So it's more like you try to use the statistics and then in order to find the probability function. So probability function actually, when I learn the probability, I take it for granted. There's a random variable x, say h, x is h. And p of x, you write quickly p of x, and so on, and say, it's a uniform distributed or exponential distributed, Gaussian distributed, whatever. You write so easily, right? But later on, I realized probability is a sort of a beautified ideal case. Actually, a lot of things you really don't know the probability. How do you know? You know it's after fact. You know statistics. You know it's really the fact. But use the fact to approximate, to find the probability. So probability really is a very abstract model. It's a very abstract mathematical model. Do you know what I mean? So probability really is an abstract model, but histogram is a statistics. And statistics is really something computable, measurable. Is that clear? Something concrete is a histogram. Probability distribution function is really idealized concept. But it took me a long time to really separate the two. In the past, I said histogram, the probability histogram. No, actually, they are two different things. Probability really idealized thing. And in the real world, it's really a mathematical beauty. It's a mathematical concept. It's not the real world major concept. Real world major concept is a histogram. Okay, so histogram really it's a measured distribution. And while probability is really the mathematical, also mathematical idealized concept. Okay, so it's related to so-called random variables. Random variables, follow certain distributions. A histogram is something you just can measure. And so there are many random variables you consider. For example, age is one thing. Another is scores, your score. So when we talk about your score, then we talk about histogram. We don't talk about probability of your score. Right? We talk about histogram of the score. The student taking exams, there are certain scores, and then we talk about the distributions, but that's major, so that's histogram. Okay, so in terms of the images, so given the images, then we can look at each pixel. Each pixel is a sample point, okay? And then either grade level then it's just, if you grade level images, so the random variables will be the image intensity. Image intensity starting from 0 to 255. right? From 0 to 255. Because each pixel can only have one image intensity, either 0, 1, 2 until 255. So 256 choices. Then I go through that. Then I can say how many image pixel has intensity 0, how many has image intensity 1, how many it's 254, and how many 255. So I can draw this kind of plot. I can draw this kind of distributions. So these are sort of the number of occurrence. Number of occurrence. And so that's called a histogram. And how you calculate this histogram? Basically, you just go to access every pixels and record that. And so if you go to, then you need an array, right? You need an array. This array is from 0 to 255. So whenever you go through one pixel, it's the 0, then you go to the 0 place, add 1. Right? And then you go to the second one. The second one say 254, then you go to 254, add 1. Initialize everyone 0, and then you start add 1, until you scan everything. Right? You scan everything, then you add value to this intensity. So you can create a histogram. So can you write a program on that? Can or cannot, you have to, right? This is part of homework. You just have to do the histogram calculation. You cannot use MATLAB to code the histogram. You just have to do the histogram yourself, okay? So you have to implement that. Usually C is using pointer, right? You have a pointer to point to 0, point to 1, point to something. So that's the histogram. But then RGB, how are RGB? So the color, then you have the 3 pins, RGB. Again, each one, RGB, you have distributions. You go through the whole images, and then you have the histogram for each one. So again, the 3 bytes, right? The first byte is R. And then the second byte is G, the third byte is B, and then go again. So each color, you calculate its distributions. So RGB, you have 3 histograms for different 3 colors. Okay, and for one given image, you have the 3 channels, 3 histograms. So now, for this particular input images, you can find, usually, just use R as example, but similarly apply to G and B. So suppose you consider R. Here is intervals. You may have a lot of spike, and then you get something in other place. So basically, there are 2 groups. Okay, so there is one group and representing the background, and there is another group representing the foreground. Okay, so then you can use your eyes to separate them, and then you can find if they are ideal case is just one value, right? But general practical case, there is a range. So then you can find the boundary between this R1. So it's R1, R2. So if you are in the R1, R2, you consider its background. Okay? So later on, when you go to pixels, then you can know this pixel belongs to the foreground or belongs to the background. If it belongs to background, you want to take it out, right? And take out, what are you going to do? So when you go to the output images, when you want to take it out, you replace by the white, right? So basically, you have input image. It's the one with the blue background, this one. And then once you do the histogram analysis, you know the R1, R2, and so on. So when you come here, this is your input image, and this is output. So go to the first one and check. If this pixel belongs to the background, if it belongs to the background, come to here and replace by white. White means RGB is 255, 255, 255. I replace, it's not replace. I just write this white. But if this one is a foreground, I just copy its original RGB to the output. Yes? Oh, right. Operator, can you show the computer screen? So, yeah. So here, this is input, and this output. So when you want to remove this background, the way you do it, you go to each pixel, right? And you check this pixel is a foreground or background. And whether it's foreground, background, you use the histogram to decide. For example, there are RGB, there's a R1, R2. So within the R1, R2, you know it's background, right? And G is within the G1, G2, and blue is B1, B1, B2. So they are in that range, it's background. So once it's background, then you in the output, the pixel location, you write its output is white. White means R, G, B all equal the biggest value, 255, 255. So you can write it here. White doesn't mean there's no value, okay? White means there is 255, 255, 255 is white. And then if you go to the foreground, you just copy RGB. Just copy RGB from the input, just copy direct to the output, that's it. But background, you just replace or just change the output to the maximum RGB. Is that clear? Okay, so that's the background removal. So you need to do some analysis, R1, R2, G1, G2, B1, and B2, before you do the background detection. Okay, so this is part of the process you are able to find the background. Next problem, identify geometric object. This is still basic 6 point. For this part, you need to write a function which counts the total number of geometric objects in the shape dot row. Okay, so this is the shape dot row. Color. The total number of squares and their respective side length. So how long is the side? How long is the side? And the total number of circles and their respective radii. What's the radius of each circle? How many circles? You can count here, right? They count 1, 2, 3, 4, right? And 1, 2, 3. So 3 squares, right? 3 squares and 4 circles, right? By your eyes. But now you need a computer to count that. How to do it? And also the total number of geometric objects is ng equal nc plus ns, right? So you use the output from problem 1a as the input to this function. So problem 1a output is this guy, right? That's the output. As the input to this problem, you can assume both circle and square are positioned at the center of the images. So they are centered around the image center. And clearly discuss your algorithm and show the intermediate result, if any, in your report. So actually, the algorithm, I give you some hint already, or the TA give you some hint. You can traverse along the image center horizontally or vertically, pixel by pixel, to identify the cross points of each object with the x-axis or the y-axis. You go from the center, image center, but you have to find the image center coordinate, right? You need to find how to find that one. Again, it's a simple one, but you need to access the center. And then you can do this kind of transverse, go this along the x-axis or along y-axis. Just search, and you search whether it's white or it's non-white, right? So you have the cross point. So you can count how many cross points you have, and then you count how many objects. And also how you differentiate the square and the circle. Square and circle, you basically need to move around. When there's a cross point, you go up, down, or you need to go through some circle. If you go up, down, it's okay. That means it's like a square, right? The boundary of a square. But you need to check the radius. The x squared plus y squared is equal constant. Then it will be circle. Right? So you need to search around the neighbor of that cross point in order to differentiate it's a circle or square. By using spatial property of this simple example, okay? Again, this I'm not testing something very complicated algorithm. I just want to know how can you do the image access and search neighbor, find the points, ij, that's all. I don't think this problem is too difficult. Or you want to find something extremely complicated. No, I just want you to be able to look at the point you can search around and so on, okay? So, where is that? So, to identify cross point of each object. And to identify the shape of object, you can transverse the neighborhood of a cross point. It's a very special case, I understand, okay? Usually you cannot detect a square using this approach. But here, I'm not going to really detect a real square. I only say there are two choices, either square or circle, and detect one of them. That's a simplified, very simplified problem. Okay? But only under the simplified case, you do this problem. Don't assume something very complicated. Okay, the last one, extracting the geometric object. Okay, again, it's basic. Besides identify the number and the shape of the object in the image. So say I have how many circles? 4 or 3? Anyway, one is 3, one is 4, right? Anyway, I just forgot. You can separate different objects. Please write a function to extract any given object, circle or square, from the shape dot row. Or you output from the 1A, the 1B. Right? The same function should be able to extract square and circle. Use this function to extract the second largest circle and the second largest square from the square dot row. Please discuss your algorithm in detail, your report, and show the immediate result if any. Hint, from problem 1B, you can deduce the diameter and side of circle and square. So diameter of a circle or side of a square, and determine the order in which they appear, right? Which order. Then you can transverse a circle surrounding the center of the images, or a square object, horizontally, vertically, pixel by pixels. Yeah, there are many, there are many objects, okay, here, but which one belong to the same group? So there are, say, 4 circles, but which one belong to the second circle? It belongs to the second circle. You need to transverse that. And how you transverse that? Basically, pixel by pixel. Basically, you try to calculate the radius, right? You calculate x squared plus y squared equal some constant. So you need to find the center, and you know their x, y, their individual ij, right? Individual ij, and you calculate distance. And then you do one by one and transverse until you come back. And all these points surrounding that will become one group. Is that clear? So this is one circle. You will not mix with other circles. But you need to pick all those points out, filter them out, and show them. In terms of geometry, this is like I would say, I don't know, it's for the middle school or elementary school. In terms of mathematics, it's just like a middle school, or maybe even lower than middle, or maybe elementary school student can do this mathematically. But here is a programming. So programming make your life is harder. But anyway, that's I intend to ask you to do. Right? Okay, so this is just, it's very simple, right? It's either x equal constant, y equal constant. That's a sign. Or the radius, you know, the radius, take your distance should be equal. You get that out. But the problem is that you need to write a program to get that out. Okay, so the transverse of an object is completed by revisiting the start pixels. So you can go horizontal or vertical at the start pixel, and then start pixel you go around until you come back, revisit that, and then you are done. Right? You can use the transversal pattern to identify the shape of object as well. Okay, so that's problem 1C. And problem 1D, advanced, 11 point, okay? So smart camera moving object removal. So Tommy Trojan, on his trip to Washington, snapped a few shots of the White House. Okay, so you want to get that. But after returning home, he realized all photos have been spoiled by a Fox Superman. Okay, this is the TA's imagination. Okay, but anyway, suppose that. So he take a quick shot, and so give it the 8 different shots, but the Superman sort of flying and in different locations, and so on. Okay, and so Tommy does not like the Foxman spoiling his White House pictures. So please help Tommy generate a picture of the White House without the Foxman. This one, there's a flaw here, okay. This one not clean, there's something here. So everyone, so every image has been been contaminated by a little bit, okay? Know that many cameras nowadays come with such a features, okay? So it means remove something, right? Remove something. So you shoot many things, but you can remove the moving part. The moving object can be removed, and you get the still background. You can use simple image manipulation to solve the problems. You may first detect the common content of these multiple images, and then fill in the area occupied by the Foxman with proper content. Usually it's called the image inpainting. Image inpainting means you want to erase something. Then basically you need to find the background. But the challenge of image inpainting is only given one image. Say there's a waterfall and someone jumped from the rock to the pool, okay, to the lake or whatever, the waterfall. But you want to remove that person just to see the pure waterfall. There's called image inpainting, but single image. But here I try to simplify it and so on. So I'm really not teaching you the image inpainting technique. But the general technique called image inpainting is remove some undesirable object. So this is also known as the image inpainting techniques, but it's much deeper one, but rather than this simple one. So images in figure 3 are generated. Actually, the TA generate these images by putting a Superman on top of this White House. Okay, so it's this really artificially made. Okay, but now you need to recover based on this 8. You need to recover this one. So image of figure 3 are generated using the blue screen technique. Okay, so the TA using blue screen to get the Superman, and then put the Superman overlay with the White House. And finally, Tommy wants to create a fun photo. Okay, that's the next part. Okay. So how to do this? How to do this? Let me give you some hints. Okay. So all these images, we assume very simple case. The background is still. There's no movement. If there is some translational movement, we have to move the background a little bit. But here, let's assume the background all the still the same. So you can do subtraction. For example, you can do subtraction for any two, or you can do subtraction something far away. For example, you subtract this from this. What will happen? Most part will be 0, right? So 0 means the content is the same. But this part will be non-zero. This part will be non-zero. So the non-zero part will be something you need to fill in, right? But you can use this two, and this two to say use the other two, for example. Suppose you use this one and this one. And this one, you also get the 2 parts destroyed. The other part is clean. So then this part will be clean for this guy. Okay, maybe there's not. Why not try this too? Try this too. This part will be clean in both. Right? So this part needs to be handled, but this is clean for this part. So you can get the clean part from these 2 images to cover this. And this is not clean, but this 2 will be clean for this part. So you can use this 2 to fill in this part. Right? So when you do the 2 image subtraction, you are able to get a common part. Common part means 0. They are identical. And there are some part, one has a contaminated by one thing, there's another contaminated by something. That part will be no 1. Okay, not 1, not 0, sorry. Non-zero. A non-zero means it's something just you don't know. Okay, but you do another combination, you have some holes. But those holes you can borrow from the place which is 0. Then you can use that part to fill in. That's all. So this is, again, it's about the image access and writing. I'm not talking about any fancy algorithm. Can you follow me? I'm not talking about fancy algorithm. I'm just talking about, can you manipulate image in a simple way so that define the part you don't like and the part you like and replace them. That's all. So don't feel this really that tough, okay? Another one, next one. Finally, Tommy, actually this should be another line, beginning of now, wants to create a fun photo in which the Superman is being jumped over by a dog. So the Superman is flying, right, very, very happy, but somehow the dog jump over that, make the Superman look bad, okay? But anyway, so you want to make a fun photo. To achieve this goal, you should first extract Superman's photo from figure 3. So you need to get the Superman out. Okay, first you get Superman out, and I tell you how to do it. Okay, this is the most complete. These two are complete. These have been cut. Okay, these are also complete. These are complete. So these three are complete. These are cut, partially cut. So you have to figure out how to get Superman from this 5, something like that. Okay, this may be a little tougher because of the background similarity, but this is sort of very easy to find out from this Superman, right? So anyway, you need to find some Superman and then get it out, okay? So get the Superman out. Okay, once you have the Superman out, then you need to put Superman here. Insert Superman here, okay? So use the dog jump row, this dog jump row without Superman, right? To create a desired photo as shown in figure 5b. So this is like a desired output. To achieve this goal, you should first extract Superman's photo from figure 3, which should be the byproduct of cleaning the White House. If you have a clean White House, you can get Superman easily. The exact placement of Superman image in the dog row is less a concern, and you can choose the desired location with the proper coordinates manually. Please clearly discuss your approach in the report along with the final use coordinate. So basically, you want to put Superman here, but the exact location, it doesn't really matter. Okay, so you can do the things you would like to do, but explain how you put the Superman in this location. In this location. And also, if there is some overlay, you want to put the dog in front, or you want to put Superman in front. You have to explain. There are sometimes overlay, right? The dog and Superman. If there is some touch point, then you have to say the dog in front of Superman in front. But either way is fine. Just explain what you do. Tell the grader what you do. So that's about the problem number 1 of the homework 1. Okay? So if you need a warm-up, you better do it soon. Okay? And another thing I really need to emphasize is, from past experience, some student has a miserable life in this class. And the miserable life, only one reason. They don't do the homework in the first 2 weeks. They leave everything until the 3rd week, and then the homework due in 1 week. They have to do all the 3 problems together within 1 week. Then they live in the hell. Okay, their life is living the hell. And then they need a week to recover. So then again, the next 2 weeks, they don't do anything. Then they're living in hell again in the 3rd week. It becomes very malicious cycle. There are people like that. There are people like that, okay? I'm not people like that. And I hope none of you like that. You start from the first week, spread the load. Each week, learn something. Actually, it's much more solid. You push everything the last week. Actually, you're always in the rush. You don't learn much. You just get things out, okay? I hope you are mature. You are already a graduate student. You are not an undergraduate student. And so you know how to spend your time well and do things early. That's only one advice. If you do things early, your life will be much more balanced. But if you wait until the 3rd week, terrible. Okay? So this is about the first homework, and you should be able to do it. And in particular, you are not very familiar with programming. This is a good exercise. And I'm not talking about something very fancy. Just about really find the points, where to get the things, where to put. That's all. Any question about this? Okay, now let's come to the image enhancement. Chapter 1. Operator, can you come back to the notepad? Can you show? Okay, very good. So the first subject I want to talk is about the image enhancement. There are several scenarios. So basically we will cover, I will say, 2 major topics. So one is about the contrast manipulation. Another subject I will talk about is the noise removal. So these are the two major subjects. And there is some subject, small one is like try to sharpen the edge, right? So, but it's a less complicated. So it's like a little touch about edge sharpening. We'll put more focus on these two subjects. And contrast manipulations usually needed is to make the sometimes the image is very dark, or sometimes it's very bright, or sometimes it's very narrow in the dynamic range. So you don't see a good contrast. And if you can enhance the contrast, you can see a better image. Let me show you something. Okay. The next homework, the problem number 2. Okay, can you, okay, yeah. So you can see this is Barbara images, and these are all poor contrast images. This is in very bright range. This is in the middle range. This is a very, very dark range. I don't think you can see anything here. Okay. But anyway, there's still Barbara here, okay? So these 3 are all bad images. But just the grade level distribution in different places. Some is very dark region, some is very middle region, and some is a very bright region. So they all poor contrast, you know, the relative black and white, in the very narrow range. So if the grade level distribution focus in the very narrow range, then you don't feel good. You want to make the contrast bigger. Okay. So how to do that? Then you can do the histogram manipulations. And this is a similar thing for the color images. You know, how you make this color image better. You can improve the contrast much, much more, and then you see something you really like. But here you don't like. You don't really see what's going on here. Okay. So you will do something there. And similarly, there is also the high contrast, but it's too much. So you want to also make it, it's too much the two extremes, right? It's just even very bright or very dark, nothing in the middle. So in some sense, it's still narrow. But of course, this two narrow band, among them is big, but actually they are focused on the very bright or very dark regions. Also not very good. You want to make everything like in the middle as well, right? Cover the full spectrum. So this also poor contrast images. Okay, so the problem 2 is try to how to manipulate, do some image processing so that you are able to get a much beautiful images after you do the contrast manipulation. Okay, so so the contrast manipulation, come back to the notepad. Operator, can you show the notepad? The notepad, the camera above me. Operator? Someone there? Okay, good, thank you. So, so what's the principle behind the contrast manipulation? So I'll tell you something very simple in the beginning, and tell you something really the right and good approach to do it. Okay. The first one just very ad hoc. It's ad hoc, but it's at least to give you some feeling about what's going on. Okay. So there's some ad hoc approach, but try to give you some kind of initial insight, and then we'll talk something very rigorous, and you can do things much better. So ad hoc approach is so-called linear scaling. The linear scaling basically is the low contrast images. So the poor contrast is due to the low dynamic range, low gray level range of image pixels in an image. So in other words, if you have the histogram of the input, suppose there's the image, poor contrast. Right? So you look at the intensity or the gray level. You look at the histogram. So this is 0, this is 255. The distribution of this gray level is a very narrow band. So maybe here, right? Or maybe here, another, or maybe here. These are 3 cases, right? Anyway, so here you will see something very dark because it's focused on the dark area, and this is the middle red area, and this is bright area. But it's just the histogram distribution is very narrow in certain band. And you don't fully use all the possible gray level distributions. Gray level originally you have 2 to 55, but you only focus on one area. Okay, the other is either nothing or very small. The distribution is very small and focus. Then you see the poor contrast image. So that's the reason. So in order to make it a better contrast images, you want to spread that, put them sort of cover the full dynamic range as much as possible, right? So how you do that? So one possibility is to do the scaling. And scaling means, so suppose we have an input image called F. And output image is G. And suppose the input image has the original dynamic range is F min and F max. So means the gray level of image F has a certain range from F min to F max. And the output, you have the G min and G max. And this scaling function I call H. And what I'm going to do is I want to do a scaling. I try to mapping this range to this range. In a linear way. And so if I draw in F and G relationship, so suppose my original F min, F max is here. But I want my G min is here, and G max is here. Then can you see the difference? Originally it's a very narrow, but now I've become very broad, right? So dynamic range is a poor contrast, but it's better contrast. So then I have 2 points. F min, I want to map to the G min. F max, I want to map to the G max. And all the middle points follow this kind of linear scaling. So this curve we call the transfer function. So I can write down this transfer function. It's H. So G is equal H of F. And this one actually is G min plus G max minus G mean, Fx minus F mean, and here F minus F mean. This is the product. So you can check that when F equal F mean, there's nothing here, right? F equal F mean, this is 0, so it's G equal G mean. When F equal F max, this cancel out, and G mean is G max minus G mean, is minus here. So you subtract them, so you get it. When F equal F max, you get G max. Is that clear? And this is a linear curve, and this is slope. This is slope. So slope is determined by the ratio. The difference here, this is slope. This divided by this, right? So the difference divided by this difference, that's the slope. And in order to increase the contrast, the slope has to be what? Has to be greater than 1, right? You want slope greater than 1. If you slope less than 1, you reduce the contrast. So you can do that so that you are able to expand the contrast in the region of your interest. This is called linear scaling. Is this okay? This is intuitive, right? Okay, and then so you can do several things. And there may be some question you may have. You say, well, what happened here? I get a negative G. What am I going to do? And so there are several ways you can do. You can clip it. You make this like when F go lower, I make it 0. And when it go beyond the 255, I make it like, again, 0, something like that. But usually that's not good. So there are different techniques you can do. But you can read the books. Actually, this technique is, honestly speaking, no one cares. This is just too simple. It's not going to be useful. Okay, so it's just a very simple idea, okay, but it's a starting point. Starting point. So let me show you several images. The books took a lot of space talking about this, but to me, this is all trivial thing. There's no need to go over all this kind of discussion, okay? So if you read a book, actually, you feel the tempo is so slow compared to mine. Okay, so let me show you several things. Let's starting from, there's no original. Opera, can you zoom into this area? Okay, that's good. So suppose this is some input images, but it's still the contrast is very low because it's close to the bright regions. And you want to sort of enhance the contrast. But you want to enhance the contrast, you get something like that. Actually, you don't like this either because something becomes too dark. Actually, relative speaking, these two color and these two color, indeed, you increase the contrast, right? Can you see that? This one contrast, the contrast is better. But it's still not very good because the thing is, when you go beyond something, you cannot differentiate. Say you make this cover dark, but B is even darker. But B is so dark, you are not able to see the B and the book cover anymore. You know what I mean? Because you want to increase the contrast between this guy and this guy. So indeed, increase that. But once you make this very dark, this B where to hide. B will be even darker, and darker just, there's no B. And this one is try to flip around things. So when things become negative, I go to another direction. So 45 degrees, that's actually shown by this. So something becomes negative values, then you turn it around. You turn it around, go to another direction. So that's some reflection. So in this example, particularly, the B, it's become too dark. I'm not able to separate. But I go another direction, I can see the B now. I think you probably don't understand what I'm talking, right? Do you? Okay, let me slow down. Actually, there are two steps. So usually you have F go through the H, you get G, and then after G, you can do something, get a G prime, okay? If this H go beyond the range, there are two cases. So one choice is clipping. Clipping usually it's or you can do another called absolute value scaling. What's clipping? What's absolute? There are two choices. Clipping means I just whenever this is G, this is a G prime. Whenever I go to the 255, I clip it. When I go below to 0, I clip it. And the other part, I don't change. So in the previous case, when G becomes negative, I clip it, right? So when G becomes negative, the G prime just, you don't allow G prime to be negative. You just choose, when G is negative, G prime becomes 0. When G goes above 255, you make it just 255. You clip in two ends, the G prime. Okay, so this is a clipping choice here. There's another choice called absolute value scaling. Absolute value is going to go the other way around. G and G prime, you do this 45-degree line, keep the same. But then once you go to above 255, you go to negative direction. When you go negative, I go this direction. Can you see that? So when G becomes a negative, instead of clip it means I don't have any contrast. I go another direction. I still preserving some kind of thing, but it's just something darker, I make it brighter. And something become brighter than 255, then I'm not going to do even brighter. There's no room anymore. I go the other way, I make it darker. So this is called the absolute value scaling. Absolute value means when you consider absolute value, this is the plus and minus, but you consider only absolute value. And so you go look this direction, subtraction, there's you look at the absolute value. Go the other direction, it becomes like something, 255 subtract that, you get negative, but you just take the absolute value. Go down. Is that clear? So that's the final stage. So you have two stages. First, you allow something go out of the bound, go out of 0 and 255, you allow it. But then go to the second stage, you try to fix it so that you will only limit it by 2 and 55. But how to do that? One, you just clip it. But clip it, you cannot see any variation anymore. Right? Everything becomes just the same. You lose all the details. But you go the other direction, then the thing is, the color is, the gray level is not correct. But human eye feel more comfortable. So that's called absolute value. But it's small tricks. There's nothing too much to talk about. It's just small tricks. You mean the G prime? Right. These two just the people experience. People don't like this, and some people suggest this, but I will say this is just an art. I'm not going to spend too much time on this. This is just heuristic. You're purely heuristic. So nothing to talk. You just know, okay, something can be done this way, but it's nothing deep. G is just intermediate result. You don't have to worry. You don't have to show G. You just have to display G prime. Right? No, I think that the reason I want to decompose two-step, I wanted the flexibility first. So I don't need to restrict this middle result to be between 0 and 255. but then I add another stage, so rescue it, so that it will be between 0 and 255. So I only show this display, but this is like a mathematics. So it's okay, but it's not going to show in the final screen. The final screen is G prime. But as I said, this is just heuristic. You know, don't spend too much time think about this like very something, you know, it's not good, okay? This is not good. I want to talk to you something better. Okay? But there is some important lesson to learn from that is let me show you several examples, okay? So first is look at the histogram. So there's a F-16 fighter. You know, it's a military airplane. You do the histogram analysis. This is a normalized histogram between 0 and 1. So you can say 0 and 255, but you can normalize it. So the high is called 1, low is called 0. So normalize everything divided by 255. And you can see there's a lot of cloud and mountains. So you have to do something larger value in the close to 1 because the cloud and the mountain. And then there's some kind of the fighter, the tail, and the body is here. Okay, so this is the middle range for this object, and this one is for the background. But this dynamic range is narrow. You don't use the full dynamic range. You don't use something very dark, you use something very bright. Right? So the way you want to do is you want to find a linear scaling, scale this part, and so that make this and this is much broader, broader than this, right? Compared to the contrast, this range, so you get something slope greater than 1, but then clip them. So you compare these two images, now you see something here. You don't see something from here, there's nothing here, but you are able to see something in the dark regions because this part mapped to there. Something here, mapped to here, and this is darker. Okay, and you can also manipulate all this transfer function, and say you can use the square rule, square as a transfer function, and we'll use the cube transfer function. And the transfer function again, here you show you have this part you sort of reduce the dynamic range, right? Because the slope is less than 1. So it means this part actually is very few population here. So you can try to use that part, and there's more here, so you can increase the dynamic range here. Is that clear? So you can get something like that. But again, this is just very heuristic. I don't want to say too much about that. There's another example is changing the using this kind of shape. This kind of shape means something bright, but you reduce dynamic range, and something darker, you increase dynamic range. But it does not help you much because the original is very bright. So you do this, actually you cannot help much of the bright regions, right? The bright regions, you reduce it, or this one you increase a little bit, and similar to that. And this is another piecewise linear transfer function, and so on. This is called a reverse function. So something very dark, you make it something bright. Something very bright, you make it dark. So this is like take a negative. This is like a negative of this one. Something bright become dark, dark become bright. So tail now become bright, but in here tail is dark. Okay, so these are the different kind of transfer function you can talk about, but I want to make some observations. Really, a good transfer function, it should depend on histogram, right? And the histogram, basically, the histogram, if you have a lot of pixels in that range, you should what? You should sort of increase that dynamic range for that one. So suppose you have histogram. So suppose you have something here, and 0, 0, 0. If something has a small value in the histogram, something very small, then you don't have to give them too much contrast label, right? But if something very heavy, then you want to give them more contrast. So it's an allocation of this contrast dynamic range from 0 to 5. These are considered like bandwidth, right? This is a very precious resource. And which part you want to give more contrast, more range, gradable range, is the part with a lot of activity, means a lot of image pixels surrounding that. You need to want to give them more contrast. And something there is nothing going on, there is no pixels, then you can squeeze that. Agree? That's a very general idea. Okay, now let's come to something really formal. It's called histogram equalization. The best way to use the grade label, it means you have input images, you through some magic operation, transfer function, you get a G. So this is the transfer function. You want to find some magic transfer function so that the histogram, no matter what histogram in the beginning, I want my end histogram to be flat. To be flat means I use all the grade label. I use every one, 0 to 2 to 5, and each one has the same numbers. So it means if the image size is n by n, suppose this is n by n, then each value will be n squared divided by 256. So totally, I have n squared pixels, right? And 2 n squared pixels divided by 256 grade labels. Every grade label has n squared divided by 256, and equal height. Is equal. This will be the best result you can hope. If you try to use grade label, all the possible grade label equally, make them the same height. So this technique is called histogram equalization. So this one is not ad hoc. This one has a goal. So you have input, I have output, design output, and how I do design something in the middle. Agree? This is much better than anything we talked in the past. I call it ad hoc heuristic. Actually, it's you are taking a master level courses. You should much better than that. Okay? So I try to quickly go over that. I don't want to spend too much time on that. This one is more important. Histogram equalization. And when I talk about this problem, do you have anything come to your mind? This is a mathematical problem, right? This cannot be ad hocly solved. We got to have some mathematical model, mathematical way to handle it. So what comes to your brain? What comes to your mind? So what tool related to this? Integral? Can you elaborate a little more? Yeah, I think you have a high level, it's correct in the high level. Yeah, but a little bit more detail. Actually, this is one very important subject in probability. Very important subject probability. It's called change of random variables. And what do you mean change of random variables? Usually, I have a random variable x, right? The random variable x. And one way is I look at the probability distribution of x. I want to make it become uniform distributed. But most common is the other way around. So I have a random variable x with uniform distribution. That's you can use the random number generator to generate a uniform distribution random variable. And I want to make this random variable with some distribution, maybe Gaussian distribution, maybe Laplacian distribution, maybe whatever distribution you like. So starting from uniform, and you want to change the variable so that make this random variable become following certain probability distribution. You think that's a useful function? Because most cases, you just have the a random variable to be uniform distributed, but you don't have arbitrary distribution, right? But you need to figure out a way how to go from this random variable to that random variable. But that random variable is through transformation. The random x random variable y, but y is a transform of x, so that you can generate very flexible probability distribution. So that's a very important problem. But then this problem is the reverse of that. I go from very flexible distributions, but I won't make it uniform. You just reverse the process. But fundamentally, it's the same. If you can go from one to the other, you can go from the other to. Clear? So actually, this is one key subject in probability theory. So this is a key concept in probability theory. So you basically want to relate, say there's a random variable x, there's a random variable y. And random variable x has its probability density function. So say fx, and this has a probability fy. And how we do the transform between the two, and then we can shape the probability density function to the one we like. So given one, then we want to shape the desired one. So there is the input, and there's the output. Okay, and then these two are given. And then given these two, how we do the transform in the middle. Okay, so that's really a very important problem. Probably, I have to be honest, when I learned the probability theory when I was undergraduate student, I thought I did very well in all the probability, but I missed this part. I didn't know this I can learn from the class. I didn't think this, I just missed that at all, you know. I didn't, but then I pay a price. There's a screening exam when I was still in graduate school, screening exam. They asked me this problem, and I couldn't solve it. It was you know, but after that exam, I remember this so well. You paid a big price, you remember all your life. This is something very important. Just change your random variable. There's a section. Look at all the probability book. There's a chapter, there's a section about change your random variable. So changing of the random variables and so on, and then how the probability relate to each other. But to me, that's too abstract. I really cannot appreciate that formula. I don't know what's going on. No concrete examples. Right? So I just forgot that there is such a section in the book. But when the exam came, and I said, oh, I never read that section. But then I realized that section is so important. I mean, if you read it, you start a claim, you got an A in probability theory, but you don't know that section, you only deserve a B. You know what I mean? So sometimes we miss something very important we didn't know until we pay the price. So anyway, how you do this? So I don't know how many of you remember this. How many of you feel you are good in probability? No one claims they are good, right? Everyone needs to take a probability theory now. Okay, you will learn. Okay, you will learn this about this one. Okay, this is one of very important subject in probability theory. But I can tell you roughly what's this about. You are not able to see the probability density function because it's too local. It's not global. But you can see the probability distribution function. Do you know what the difference between the density function and distribution function? The probability distribution function is a cumulative one. When we say f of xx, we just say it's something like between the x and delta x. The distribution between this interval. Okay, x and x plus delta x. But when we say the distribution function, usually we use p. Distribution function usually we start from the smallest one. So usually we say starting from 0 to x. It's a cumulative function. So it means you are doing the integration of this density function from the lowest value up to the current point. You do the integration. So that student talk about the integration integral. So you look at the cumulative density up to certain point. Right? You add all them together. So it's the area. So the probability density function can be looked at this. But the cumulative function means basically it's, up to a certain point. So the probability distribution function will monotonically increase. It will not decrease, right? It's just adding. So you go to here, you add more until final point. Final point is what? 1. Total is 1, right? 100%. So this is a density function, but the corresponding distribution function is the integral of this function, and you gradually going up until reach 1. Okay? Is that clear? Not clear? Or it's okay, right? So if you come back to this concept, this histogram, if you consider doing the integration, if you consider histogram, when you do integration, if there is nothing, if you do the integration, it will be what? It will be flat, right? But if there is a lot of things going on, then you will go up quickly. And if it's nothing, you go flat again. And there is a lot of things, then you rise up all quickly and flat again. So that distribution actually is a very good transfer function. Think about that. When there are many things going on, I increase quickly, so I keep big slope. When there is nothing, I stay flat. So that distribution function actually is the ideal transfer function you have. But that's a result. That's a result. I can tell you the result. Actually, the transfer you need to do is really to do the integration. Do the integration of this. Okay. So anyway, what I can give you just a very simple plot to explain the relationship. So let me explain the relationship. Okay, x and y. So there is f. There is a probability density function. And this is G, and there is a probability distribution function of G. I think that the histogram, let me put the H. H means histogram, okay? So the H histogram, so this one is, suppose I have this one, the histogram look like this. And the histogram look like this, desired one. And then the distribution function, I look at P. The P look like and this PG the PG looks like this. This is a 45-degree line. Because the integration of this one is a 45-degree line. Agree? And the integration of this is something like that. There is something change a lot and then become flat. So integrate this like something like that. So this for this probability density function and the distribution function, and this one is for the uniform distribution density and uniform cumulative function. Is that okay? I'm not able to relate these two directly, but I'm able to relate to here. Means, say I'm reaching to a certain percent. I'm reaching 50%, for example, say 50%. My F is what? Can I also look at the 50% place, 50%, and look at my corresponding G? So then I can say the F give me the 50% should corresponding to the same 50% and then map to the G. So suppose F50, put it here, and G50. So I'm starting from any percentage, F10. So means the F10 position give me the 10% cumulative one. Then I go to the 10% location and coming down to see what the 10%. So that F10% point should map to the G 10% point. So then I can relate all this F, the input F, the grade label to the G. G is the uniform distributed. Agree? 1% I go to 1%, 2% I go 2%, 10% I go 10%, 20 I go 20%. I just want to do those kind of relationships. So that's the H. That's the H above. But I cannot do locally Because locally, I don't know where you are. I only see my neighbor. I cannot see the whole thing. I only see my neighbor. There's a big chunk here, but I don't see the global view. But here you have global view. Starting from very dark until now. And there are only, say, X certain percent. And I go there, I only see the still X certain percent, and I know the F and G. Does that make sense to you? You can do this mathematically, but here I try to just using something simple. So this PF is really the integration from 0 to certain value, and then I do the HF. So I put tilde here. I put tilde here. DF. So this is the integration of this guy, and PG but you know this particular is a constant. So the constant basically is just to give you this guy. PG is G. So this is a 45-degree line. 45-degree line. And you want to set them equal. So we require these two are equal. This is a cumulative function. And so this is equal G tilde. Okay? So that eventually, so we can say G tilde is equal PF inverse. No, just PF F. So in other words, H is equal PF. So this is basically the proof I'm talking about. You wanted the cumulative function to be the same, right? So the cumulative function up to the F tilde is the same as the cumulative function to the G tilde. But G tilde is uniform, so this is equal G. So in other words, this is the output you want, and this is input, and this is transfer function you are looking for. So this transfer function actually is the cumulative function. So the desired transfer function actually it's the same as the probability distribution function. And which is the, so which is the basic integral of the histogram. How many can follow you? How many cannot follow me? So if you can follow me, you raise your hand. Not too bad. How many you cannot follow me? I think my suggestion is you really go to the probability book and read that, how you change one random variable to uniform distribution to something non-uniform. Read that section. Yeah, because this really not, in some sense, is not my responsibility. It's you really need some mathematical background in order to understand the subject well. I try to explain, but there's only so much I can do. But in terms of the, I want to give you some examples, and then you can have a more feeling about that. Let me show you the result, okay? So just some proof to at least using the example to explain what's concept. This, the fighter image we showed you before. This is after histogram equalization. Actually, in this particular case, it may not look very pleasant, okay? But if you look at the computer screen, it's much better. This is just through the printing book and so on, so it doesn't look as good. But this is the equalized, the histogram. And this is the input. What's the transfer function? The transfer function happens to be this guy. This guy will give you the equalized histogram. Okay, if you look at histogram, it's equal flat. It looks like this. And this function, how you find this function? This function is the integration of the histogram of this function. So remember this one, right? And look at this histogram. So this one, you do the integration of this one, compare side by side. You do the integration, no, you don't need to zoom out the camera. Yeah, just try to keep these two images. So you integrate here, you get a flat, then you start to get something, you go up, and then this part go the highest, because you integrate this the highest, and then you have nothing, you get a flat. So this is the integration curve of this one. This is a histogram, this is the integration of histogram, and which is the transfer function. And this transfer function will give you uniform output. The output histogram will be uniform. And at least I think you will agree with me, if there is a lot of activity, you need to make slope higher, right? If there is not much activity, you want to make slope lower. And who can do this? Happen to be the integration can do that. And happen to be that the transfer function is the one you're really looking for. Okay? Okay, so anyway, you take a look at the probability book on this chapter, on this particular section. I think this is the section, and read that, try to digest. And I want to also tell you one thing, it's about the discrete implementation. Actually, this discrete implementation becomes so easy to understand. Otherwise, what else can you do? Okay, so I will tell you the discrete digital implementation. So far, it's mathematical. So this gives you some kind of one grade level in the, so there's a F and there's a G. And this H is become adaptive one. Adaptive transfer function. Adaptive in the sense, it's adaptive to the input image histogram. It's depend on the input image histogram. Okay? Because it's the integration of the histogram of the input images. So it depends on that. So it's adaptive. But it makes this final, it's a flat histogram equalized. Okay. This is, but this is one-to-one. So there is one F, there's one G. So say here you are certain value, and you find the output value. If it's not an integer, you want to find the nearest integer. So you can round off. So say pixel 15, go to which pixel. If it's 17.8, then you go to the pixel, the grade level is 18, right? 17.8, you cannot, so you go to the 18. So it's one-to-one. One pixel go to one pixel. But there is a problem for that. So it's a one grade level value. In F, you go to the one grade level in G. So one-to-one mapping. But then there is a problem. It's called the discrete contour. Let me show you these examples. So this is an input image histogram. This is a transfer function doing the integration. So you integrate this part, you go quickly up, and now go flat, and then this one you go up, and then nothing, right? So this is a transfer function you want. But when you do this transfer function, the mapping from here to here is this guy. You say, well, why is not flat? Because there is a high value in some input, some grade level, some very high value. This high value will be preserved, right? But if you look at the neighbor region of that grade level, it will be 0, 0. But there's something very high, but then the neighbor is 0, 0, right? So if you consider averaging it, it's still like flat, but actually it's discrete. The reason for discrete is you cannot show it because there are only several grade labels has value. There are a lot of no values. So when you come here, you map 1 to 1, you will you get a space, you get a 0. You cannot make everything there. You know what I mean? You are not able to, because there are only several grade label non-zero, and there are other zeros, and where you make the other zero go, the value with the 0 histogram. They have to go somewhere, right? So now it's spread in the middle. Those 0 histogram grade label will spread in the middle. Okay? So you don't really see the flat spectrum. You just see some high peak with 0 in the adjacent, in the neighborhood, and high peak, high spike with some 0. But it's really not equalized histogram. And then you see this image. Sometimes you see artificial contour. Why you say artificial contour? Because originally they are really very close to each other. But you split them, then there is a certain distance. For example, 15, next one maybe 20. There's 5 pixel, 5 grade level difference. Originally they are adjacent. But you pull them away, then suddenly you create a gap in the grade level. So then you see the artificial contour. So this is really not very good. Can you follow me? Because there are only something originally are very close to each other, right? 15, 16, 17, 18, they're close to each other. But you pull them apart. You create 0, so the gap between the grade level becomes bigger. Original continuous, now it's not continuous, it becomes discrete. There's a delta in the grade level, right? So it's not very good, but this according to what you describe, that's something you can do. So we will do something better, and there's a digital implementation. The digital implementation actually is very interesting, and actually is more intuitive. So you look at the input histogram, input image. You cascade the histogram from lowest to 1. So there is certain histogram, there are certain pixels, their histogram is 0. For example, okay? And these are their corresponding pixel values. ij, there are some ij here, right? There are several ij with histogram 0, grade level 0, and then there's something with grade level 1, and there's something with grade level 2, and so on. And maybe there's nothing with grade level 3, and then next one is 4. Can you cascade them into a long 1D array? Starting from the lowest grade level, 0, and 1, and 2, and 3, and 4, and 5, until the final one is 255. And each location, you know what the pixel it is. So the pixel may be starting from that location, from that location, from that location, but they're all 0. And then I get another one, it's a grade level 1, but from that location, that location. So each data is a coordinate. That coordinate means the image pixel with that grade level, right? And you order them according to the row-wise one. If you want to do histogram equalization, what you should do? Once you have this 1D chunk, right, you just cascade things together, and then you divide things equally. For whole thing, you get totally how many positions you have. You have n squared, right? Because you have n squared pixels. So you adding them together should be n squared. Because totally you have n squared, so you got to n squared. Now, I cut it uniformly to 256 pieces. I just cut uniformly. So this one, cut it, this one, cut it. Each one got to be, each small segment is this one. I cut it uniformly, and then the first one I call it 0. The second group I call it 1. The third group I call 2, 3, and so on. Can I do that? And then all those within the 0, those pixels, now the new value will be 0. The second group, all those pixels in the second group I call it 1. Isn't that the histogram equalization? It's a histogram equalization because I order the grade level from the smallest to the biggest. I order them this way, right? From smallest to biggest. And then I change it away. I still have order from the smallest to biggest. But the thing is I partition them, I just partition 0, 1, 2, 3, 4, 5. But this digital implementation still follow the distribution, still the same. But actually, it's much easier to understand this way. So you may not forget, you may not remember all the mathematics, but this one I explained. Can you accept this one as a histogram equalization implementation? This is the most trivial one. You just cascade them from smallest to biggest, and then redivide it, and each one is the same length. Then that's histogram equalization, right? Okay, and in that case, there are sometimes some pixels here. These pixels actually will be the beginning part. Beginning part means what? You scan according to order, right? Because there's one here, but you're starting from this. The first one is you scan the first one in the row-wise order. So there is scanning order. But when you cut it, you have the sum will go to first segment, some will go to the second segment, but according to the order. So part of them will go to 0, part of them will go to 1, divided. But it's okay. Some people try to do fancier job called randomization. So there's a total one, and I randomize it, and some give you a probability. I think it's too complicated. Forget it. I don't think that's needed. That's a small fine tuning. Okay. So basically, this is a digital implementation. Actually, this is so easy to understand compared to all the integration. I know particularly computer science students hate the integration because they haven't seen integration for years. And suddenly see integration, they feel scared by that. Okay, so that's one. And then I think, actually I'm ready to go to the problem number 2. We still have 5 minutes. Let's go to the problem number 2, okay? Let's go to problem number 2. Okay, problem number 2, image enhancement. So in this problem, you should apply the histogram manipulation for image enhancement. First is for grayscale images. It's a basic 10-point. Please implement the full range linear scaling method. Full range means the output should be the full range, okay? And the cumulative histogram equalization method. So that's what I just explained. So I explained it too, to enhance the contrast of the 3 Barbara images in figure 6. So these are 3 Barbara images. Describe the procedure and show the resulting images. And comment and compare the performance of these 2 methods. Plot the histogram of all images. 3 input and 3 output. Okay, so you have 3 input images and 3 output images. And the transfer function. So actually, the one method, you go from this, and then you have two methods. One is linear scaling, one is the histogram equalization. So you have 3 input, each one has two methods. So total you have 6 transfer functions. And MATLAB user cannot use the function in hist, right? This is related to the histogram calculation or other similar function from image processing toolbox. I use histogram show, it's okay. Show histogram. That's show histogram is okay, but calculate histogram is not allowed. Okay? You need to find how to implement that. Okay? Again, you are not users of image processing tools. You will be the engineers to create tools for people to use. So if you say I cannot do histogram calculation, then you will not get any job offer. Just too bad. So how can you know how to do that? Okay, so you got to know. You say, well, there are a lot of tools. Why cannot use? No, you are not users. You are image processing engineer. So you are engineer, not users. Okay, so histogram for color images. Please implement 2 histogram equalization methods. So one is the equalize the cumulative histogram. This one basically is a mathematical. Means I try to do the one-to-one mapping. One-to-one mapping. That's mathematical. Another is the equalize histogram method. This is equalize histogram is digital. So histogram really equalize. Okay, so that's a digital one. That's what I'm talking about. The second one. The first one is talking about mapping. You need to have one input mapped to one output, one F, one G, one F, one G. So sometimes you get the high spike with 0 in adjacent gray labels. Okay, adjacent term gets 0. So the output really not flat. The output just some high value, some 0, some high value, and 0. Averaging sense, yes, average is like flat, but locally not flat. But the second one is really flat because you really purposely design that to make it flat. So there are two methods: enhance the contrast of the ocean images. Okay, and actually you really need to do is you can do RGB separately. One for R, one for G, one for B. And histogram equalization can be performed separately, and compare and comment on the output image and equalize histogram of the two methods. So the first method and the second method. So the first method, as I said, sometimes you will get an artificial contour because they are very close in original images, but you split in the equalized histogram. So they actually create a gap between the values, RGB values. So these are low contrast ocean images. Histogram transform. Okay. All histogram equalization method you have implemented to both points can be considered as a histogram modeling, where you try to match the histogram of the source image to a target histogram, which happens to be uniform distributed. Equalized histogram, that probability of any intensity will go to this uniform way. So the intensity will be the uniform over this range. However, it's sometimes desirable that the target histogram can be of specific shape, not necessarily flat. So here you will implement one such algorithm by matching the histogram of high contrast. So this is, again, it's just a two bump, okay, Barbara images to that Gaussian distributed function. So instead of get a flat, I want to get the output is a Gaussian function. And the probability density function of Gaussian function looks like this. And construct and plot the target histogram of the 8-bit image using the equation 1. And you can use the mean mu is the mean sigma is standard deviation, right, this value. So you want the mean surrounding at 70, and then there's the Gaussian distribution surrounding the 70. Since we're 8-bit image, we will truncate the PDF outside 0 and 255. Due to truncation, the PDF may not sum to 1, so we have to normalize it again. Plot the histogram of the high contrast Barbara image is shown. So first you find the histogram here, and then conduct histogram transform, make it Gaussian, so that the contrast enhanced Barbara image has a histogram similar to the Gaussian form with the mean, mu, standard deviation, sigma. Please discuss your method with help of plot for the output image, transfer function, and enhance the histogram. Repeat the same procedure with the mu equal 120, 120, and sigma equal 50. Compare these two cases and how to modify the mean and standard deviation affect your result and why. And feel free to play with parameter if needed. Yeah, I'm running out of time. Any questions about this? So you know the law of the course is high, right? You know that now. So my only suggestion, advice is start homework immediately. Start homework immediately. Then you will be happy. Okay, you will be happy.
This concludes EE 569 on Friday, August 30th, 2013.